In the last class, we had talked about the miracle algorithm for YODA, and we said that we end up with a log likelihood function which has this form. So this is the first log likelihood function corresponding to the S1 solution. So we said if you have solutions S1 and S2. Okay, so the log likelihood corresponding to S1 after n rounds would look like this. There is some constant over here which we'll ignore for the time being. But what we have here is essentially the votes for S1 in round J. So the number of votes, you just take a square of that and subtract out the square of the number of votes for S2. Right? And similarly we have L2N. It's just where these two are replaced, these two are interchanged. And what we do is we continue from one round to the next till one of these exceeds a threshold. And if it does that, then we stop and we declare that particular corresponding solution to be the correct one. Okay. So this is what miracle was, and it has some advantages about the method in TrueBit. So the method in TrueBit, we said, could not work for a Byzantine adversary, whereas this is designed for a Byzantine adversary. In addition, we don't have to worry about too many people challenging, or whether somebody challenges or not. So we choose, of course, here unlike TrueBit where you just have a single solver, here there is a subset of nodes which we said called the execution set, and everybody in the execution set is going to execute the CIT and submit the solution. Right? So Byzantine nodes in the execution set may not submit a solution, or they may submit a wrong solution. Okay. So this was the miracle algorithm. It had a lot of advantages over the TrueBit solution, but some questions remained unanswered. So we said, for example, we said that Fmax is the worst possible fraction of Byzantine nodes in the execution sets, which we had assumed, and F is the actual fraction which could be less than Fmax. And it could be much less than Fmax, and in that case what happens? So let's think about it. So let's go back to this and let's ask one question. What if let's say the actual fraction is much smaller than Fmax? So what we said is we choose the execution set size depending on how many rounds we want to this miracle algorithm to take on average. Right? So let's say we design for an expected number of rounds to be 5 if F is equal to Fmax, and based on that we choose this execution set size. So the larger the execution set, the fewer number of rounds you need before you will converge. But of course there are more votes which are submitted in each round. Right? But the question is, what if F is much larger than Fmax? And let's think about it. So ln has this form which we've shown above. And we sum over all j. Now if F is much larger than Fmax, what does it mean? It means that you choose a particular execution set. So these are chosen randomly from among the whole stake pool. So the number of Byzantine nodes effectively would go down on average, right? So we are randomly choosing the fraction of Byzantine nodes in the execution set is also going to be smaller if f is smaller, right? Recall that f is the fraction of Byzantine nodes in the state, right? Okay. So let's say suppose S1 is the correct solution. Right. So that means these are all from the Byzantine nodes. So we are assuming, of course, that all Byzantine nodes vote for S2. And effectively what we are going to do is we are going to check whether this is greater than the threshold or not. So we start out with j equal to 1 and we calculate the likelihood, and then if it is it's not greater than the threshold, we continue to the next round and so on. So if f is small, that means these number of votes are also going to be smaller, right? So if this quantity is smaller, when f is smaller, that means this likelihood is going to cross the threshold faster. Okay. So we can say that L1n crosses the threshold T1 faster if f is small. Okay. And hence we converge in fewer rounds. Right? So that's what we wanted to do. We wanted to design for the worst case, but in case the number of Byzantine nodes is much smaller, then we converge faster. So for example, you design for let's say converging in 5 rounds, but if f is, let's say, close to 0, much smaller than f max, then you might converge in 1 round or 2 rounds. Okay? And hence we make the claim in the paper that the miracle is adaptive. Okay. So this was a good property to have. Now we have to look at another question. What if the adversary submits more than one false solution? So what if the adversary submits, let's say, L-1 solutions? So let's say we have solutions S1, S2, S3 and so on up to SL. So in case the adversary submits multiple false solutions, what do we do? Because till now we have assumed that only a single false solution was submitted, in which case we had 2 likelihood ratios. So now what we do is we extend to not just two type hypotheses, but we have L different hypotheses. And effectively HK means that SK is the solution. K goes from 1 all the way to L. Okay. So we have L hypothesis tests. So effectively we create L pairs. Okay. So previously we had S1 and S2. So we said that H1 meant that S1 is the solution, and of course H2 meant S2 is the solution. Here we are changing things a little bit differently. We are saying we are looking at a particular solution and we are saying, is it the right one or is it not? Okay, so we have L hypothesis tests, okay, and we are sort of trying to say which of these two at any time is correct. Okay, so it's previously we just had a single hypothesis test, and now we have L pairs of hypothesis tests, and we want to say which of these is correct. Okay, so as we get into the details, it will be clearer. So we have a log likelihood ratio. Which is given by this, similar to what we had earlier. And as you can expect, we want the votes for the kth solution in the jth round. Okay, and here what do we do? Right, previously we just had C1 and C2, so was just one term over here. Now we are going to club all solutions other than this solution. So we are looking at all votes other than K, and we are sort of grouping them into one and taking the square. And of course here we have that particular constant, which is the same as the constant we had in the earlier likelihood ratios. Okay. And what we are going to do is we are going to compare this likelihood ratio to some threshold. Okay, and if this is true, then we declare K as the solution. Okay, so we are clubbing all the votes here. Okay, and this threshold is nothing but what we had earlier. Okay. So suppose the attacker submits a single solution, then you can clearly see that this boils down to the same as what we had earlier, the same likelihood ratio formula. Okay. So what we should ask ourselves is, first of all, is it optimal when the attacker submits multiple wrong solutions? Okay, and the answer is that we don't think so. We are not sure. Maybe not. So one reason is that we are clubbing all of these together. Maybe that's not the best thing to do, So given the fact that the attacker is submitting multiple other solutions, maybe we could exploit those to do something else, right? But anyway, this boils down to what we had earlier, and the solution for, of course, two cases was optimal, we said, where there was only one wrong solution. For this one we are not sure, but it boils down to that case in case we just have two solutions. Okay. And other question is that here is it possible to declare multiple solutions as correct using this method? Because we have L1 to L sub L, right? We have L1, L2, all the way up to L. So the question is, can two of these cross the threshold T at the same time? And we show that that is not possible. So this is what we show on the paper. So we are guaranteed that we are going to end up with only, we'll at most say that one of them is the solution, right? Then the other question is that given that we have this particular algorithm for miracle, when multiple solutions are submitted, what should the attacker do? So what is the adversary's optimal strategy? So this miracle algorithm is known. This is the generalized version of miracle, where you have any number of solutions submitted by the adversary. So what should he do? So should the attacker submit S2 in one round and S3 in the next round? Should he submit 3 solutions in a particular round? So what should he do? What is his best strategy? And let's think about it. What should he do? Okay, so essentially what we are going to do, what miracle is doing is it's going to wait till one of the likelihoods crosses the threshold. So suppose S2 is submitted by the Byzantine adversary. So what is L2 of n? That is the constant multiplied by C2j square minus okay. Now the adversary would want one of his likelihoods to cross the threshold fast, right? I mean before, let's say, L1 of n crosses the threshold. But think about it here. For the adversary, what is there in this? There is C1j, but there is also C3j and C4j and so on, which are submitted by the adversary. Now if the adversary submits many solutions, he is actually pulling down the value of his own likelihood for L2. So he is hurting himself. He is reducing his own likelihood, this particular likelihood L2, right? And similarly, if you consider L3 and so on, that would have his votes for S2 and S4 in this particular component. Okay, so by the adversary submitting multiple solutions, he is effectively hurting himself. He is pulling down his own likelihoods, the likelihoods corresponding to his own solution. Okay? Whereas it doesn't affect L1n at all because there, no matter how he votes, all of them are clubbed together. So let's look at that. L1n has the constant C1j square minus right. Okay. So it doesn't matter to the attacker, to the honest people, how the attacker votes, because all his votes get clubbed up together over here, whether it's this, he says, submits a single solution or multiple votes. So this is unchanged. Irrespective of how the attacker votes. I should say how many solutions the adversary submits. Okay, whereas the attacker's own likelihoods are going to come down if he votes among multiple solutions. Okay, so of course we are assuming that the adversary is always submitting wrong solutions. He is not voting for S1, right? Obviously, if he votes for S1, then it hurts him because it would push up this likelihood for the correct solution and it would pull down all his own likelihoods. So the best strategy for the attacker is to vote for a single solution, always the same wrong solution all the time. So a single wrong solution is what he should submit, and always vote for this. So don't remain silent or don't vote for the correct solution. So by all Byzantine nodes in all rounds. Okay. So the interesting thing that we note here, so for multiple solutions actually we don't know and we don't think that a miracle solution is optimal, but miracle is optimal for two solutions. I should say optimal for a single Byzantine solution. And the interesting thing to note is that the Byzantine nodes, the optimal thing for it, Byzantine adversary to do is to submit a single solution. So optimal strategy Byzantine nodes is to submit a single solution. Okay. So very nicely we've sort of tracked the Byzantine adversary, right? And remember that our strategy is, the algorithm is not going to change based on what the adversary does. The algorithm is fixed. But interestingly, the adversary, if he wants to maximize his chances of winning, he should submit only a single solution. And for that particular strategy of the adversary, we are optimal. So it's sort of like we've trapped him into our design space for which we have chosen an optimal solution. Okay. So there are a few other issues which we need to consider. How would we choose this execution set? Okay, so how do we choose the execution set? And also what if we allow rational nodes among the stake pool nodes? So if we replace honest nodes by rational nodes? So I would say that our paper is one of the few papers which actually looks at this issue, and a lot of the other papers in security conferences and so on just look at honest and Byzantine nodes. But really what we should look at is rational, because in a permissionless system we can't expect people to be squeaky clean and honest all the time. But it's reasonable to think that they are rational. They would want to maximize their earnings. Okay? And what happens in that case? So in that case we are changing the threat model, and we would have to see what happens when we use miracle and so on. So here what we are going to do is we are going to use game theory, and also we are going to so we're going to use things like Nash equilibria and so on, right? And we are going to come up with a new algorithm called the Rice algorithm, which is going to help us. And here we are going to leverage some ideas from Algorand. So we'll study Algorand a little bit in detail in the later on in the course. But we'll borrow some ideas right now to say how we choose this execution set, because we want it to be chosen randomly. Let's answer this first question now, and in the next class we'll start looking at the second question where we change the threat model. So we have the stake pool over here. So these are the various nodes in the stake pool. So anyone who has deposited some money in the blockchain can become part of the stake pool, right? So that deposit will be used in order to punish somebody who misbehaves, right? And it also takes care of the Sybil issue, where one person shouldn't be able to arbitrarily claim to be any number of other people. He has to deposit a certain amount of money, and of course, depending on how much money he deposits, he can control multiple nodes in the stake pool. Right? But we are assuming that at most F max fraction of these stake pool nodes is Byzantine. So what we want to do is that given a particular task, we want to randomly choose an execution set. Given a CIT, we want to randomly choose the execution set, and we want to choose a random execution set in every round. So how is this to be done? It seems a little bit tricky because there has to be some sort of rules which everybody agrees to. I mean, it's not that each person on his own decides whether he's part of the stake pool or not. We don't want that to happen, because in that case the Byzantine adversary might always choose himself, right? So there have to be some rules for whether a node is in the execution set or not. And how do we do this? The thing is, if it's like a deterministic rule, then how is it random? I mean, and if it is random, then the question is how can you have rules to do that? Because where is randomness in a blockchain? There is nothing seemingly random in the blockchain. So one thing that we're going to use is for randomness, we're going to use the hash of blocks. So while solving the proof of work puzzle, there is some random hash value of the block which is going to be generated. We know that the hash is going to be less than the threshold of the proof of work puzzle, but we don't know what that is going to be. Still, the range is quite large from 0 to the threshold for which the hash of the block has to lie between. Okay? So just a recap, if this is the space of hash values, we said that the block hash has to be less than this threshold. Right, and effectively we don't know in advance what it's going to be, but it lies somewhere randomly in this range. Right? So we're going to exploit that. Okay? And also the question is, can we do it in such a way that nobody knows who is in the execution set? Okay, so so that's sort of an additional layer which we put in. Can a node in the stake pool know that it is selected for the execution set, but others not know. Okay. So how is this a good property? So of course a node needs to know whether it's in the execution set so that it can do the computation and submit its solution and so on. Right? But why would we not want other people to know who is in the who has been selected? Well, at least temporarily that would be a good property to have, because otherwise somebody might do a denial of service attack on that node. So somebody might know that this particular node has a certain IP address, suppose they know, right, and they know that this node has been selected in the execution set. They might do a denial of service attack to prevent that node from actually submitting its solution. Okay, so there are all sorts of attacks possible. The more complicated you make it, the better. And because Satoshi solved a lot of problems in a very simple way, we might think it's trivial to do it, but it's non-trivial. So in Satoshi's case, you can't do a denial of service attack on a miner who's going to generate a block, because you don't know who's going to generate it. You would have to do a DOS attack on all miners if you want to prevent somebody, let's say, from releasing his block or something like that, right? Okay. Anyway, so how are we going to achieve this? And lucky for us, the Algorand folks had thought of this in their solution, and we'll just briefly describe what we can do. We are going to take some of the concepts which they had presented. So let the CIT be Y, and let the CIT be in some block B. Okay. So now what we want is, we want the execution set to change for every CIT, right? And we want to include some randomness. So the CIT itself doesn't have any randomness. I mean, in theory, you could submit the same CIT later on also, right? Same computation. So what we are going to do is we create some X, which is hash of the block. So this is unpredictable. And we concatenate Y, which is a CIT, and we concatenate the round number I. Okay. So X is typically, it's going to change for every CIT, and for every round it's going to change. Okay. So this X is I would say it's a pseudo random number. Now how does a node use this X to decide whether it is part of the ES or not? So these are, let's say, some particular node in the stake pool. How does it know whether it is elected to the ES or not? So this is the ES execution set in round I. How to know that I belong here or not? Okay. So suppose a user in the stake pool has deposited money with keys, let's say SK and PK. This is the public key, and this is the secret key. So now we want that particular user, let's say some particular user U, we want it to know that it has been selected in the execution set for that particular round, but we don't want anybody else to know. Okay, at least initially, at least we wanted to be able to submit one solution before anybody knows that it is part of the execution set. Okay. So how do we do that? So let's say that the user signs X. So this is known to all. Okay, because the hash of the block is known, Y is known, and so on, right? So a block containing Y has already entered the blockchain. Right, and immediately we start the rounds. I is equal to 1 and so on, right? And later on I is equal to 2 if required to go to round 2 and so on, right? So if this signature, so he signs with the secret key, if this is less than a threshold, then the user is selected. In this execution set, right? So any user can just get his signature, and he knows if he is selected or not. Okay, and at the same time, nobody else knows what the signature is going to be because they don't have the secret key, so they don't know if a particular user is selected or not. Okay, so that gives us the property that we wanted. Okay. So later on, how do people know if this particular user was in fact correctly in the execution state? Okay. So once the user reveals this signature, then all can indeed verify the user is in execution set I. Using what? Well, suppose the user says that here is my signature for X. Everybody knows what X is. All they have to do is they have to verify that this is indeed a correct signature using this public key. Okay. So initially, before the user has submitted his solution, nobody knows that he is an ESI, so nobody can do a DOS attack on him, right? But at the same time, once he submits his solution, he can also submit this signature, and he can prove to other people that he is in the execution set. Okay. So anybody can verify that indeed he is in this set using his public key, right? So the public key can be used to check that the signature is valid. Okay. So this idea is not completely new. It's already there in the Algorand paper, and we'll discuss it in some more detail when we talk about Algorand. Okay. So to summarize Miracle, so Miracle is designed for any number of solutions submitted by the attacker, but the best thing for the attacker to do is to submit only a single wrong solution, and in that particular case Miracle is indeed optimal, what we showed. and we can design for the worst case Fmax. We can say that we are designing so that we terminate in, let's say, 3 rounds or 5 rounds or whatever. But it's adaptive. If in case the adversary's presence in the state pool is much smaller than that Fmax, we actually terminate much faster. And another advantage maybe which I haven't mentioned till now is that we don't have this whole business of the miners deciding who is right, a challenger or a solver, you know, and doing some sort of binary search and that sort of thing, which was a very tricky thing to do, which takes order of log n steps and requires the miners to actually do a computation to go from step E to step E, from step E minus 1 to step E and so on, right? So we don't have all of that here in Miracle, and Miracle works for a Byzantine adversary, right? Which we saw that Probit doesn't work. Okay, so what do we do when we change the threat model and we say that all nodes who are not Byzantine are rational? So we replace honest by rational node. Then what can we do? Okay, so it turns out that dealing with rationality is non-trivial because in theory rational people are open to bribes. So if you say a rational node is one who is going to maximize his profit, somebody can always offer a large enough bribe and get them to behave in a Byzantine manner. Okay, so we'll have to put some restrictions. We'll have to prevent disallow arbitrarily large bribes, or at least have a mechanism to deter such bribe attacks. But there are also other things that can happen. In rational nodes might, what if they collude with each other? You know, what happens then? So how do we dissuade collusion? So we'll consider new threat model, but at the same time we'll try to reduce the attack space, and we'll see what can be done, and we'll do that in the next lecture.